Welcome! In this session, we'll explore problem number 1028, recover a tree from preorder traversal. We'll break down the problem, discuss an approach to solve it, and analyze its complexity. Let's dive in. In this problem, we are asked to reconstruct a binary tree from a string representation of its preorder traversal. Preorder traversal means visiting the root node first, followed by the left subtree, and then the right subtree. Here, the input is given as a single string where each node's value is a positive integer. To indicate the depth of a node, the string uses dashes. For example, a node at depth 1 is preceded by 1 dash, a node at depth 2 has 2 dashes before its value, and so on. The problem guarantees that the input string represents a valid binary tree. Our goal is to recover this tree and return its root node. The output of this problem should be the root of the reconstructed binary tree, represented as a tree node object. Let's look at an example to understand this better. Suppose the input string is 1 2 3 4 5 6 7. This string represents the preorder traversal of a tree. The output for this input would be the tree structure in level order 1 2 5 3 4 6 7. The tree constructed from this input string has 1 as the root node, with 2 as its left child and 5 as its right child. Both 2 and 5 have their own subtrees. In this example, the root node of the tree is 1. Node 2 is the left child of 1, and node 5 is the right child. The left subtree of node 2 contains 2 children, node 3 is the left child and node 4 is the right child. Similarly, the right subtree of node 5 contains node 6 as the left child and node 7 as the right child. This example illustrates how the input string, with its dash-based depth encoding, maps to the binary tree structure. Now let's consider another example. Here, the input string is 1 2 3 4 5 6 7. The output for this input is 1 2 5 3 0 6 0 4 0 7. In this tree, the root node is still 1, with 2 as its left child and 5 as its right child. However, the structure of the subtrees is different. The left subtree of node 2 only contains node 3, which itself has a left child, node 4. On the right side, node 5 has a left child, node 6, and node 6 has a right child, node 7. This example demonstrates how the depth encoding can produce trees with varying structures. Additionally, the problem includes several constraints and edge cases to consider. For example, the tree can have up to 1,000 nodes, and each node's value is a positive integer between 1 and 10 to the power of 9. The input string is always valid, meaning it will correctly represent a preorder traversal of a binary tree. Edge cases include a single node tree, represented by the input 1, which outputs 1, or a left skewed tree like 1-2 3 4, which outputs 1 2 0 3 0 4. Another edge case is a right skewed tree, such as 1-2 3 4 5, which outputs 1 2 0 0 3 0 0 0 4 0 5. These examples cover scenarios where the structure of the tree is highly unbalanced, either leaning entirely to the left or the right. When considering how to reconstruct the tree from the preorder traversal, one intuitive approach is to use brute force parsing combined with recursion. In this method, we analyze the input string to identify the depth of each node based on the dashes and then recursively build the tree. The key insight here is that nodes at the same depth appear one after the other, so we can detect transitions between parent and child nodes. To achieve this, we can either use 2 pointers or slice the string repeatedly to locate the next node to process. While this approach is conceptually straightforward and closely mirrors the preorder traversal process, it comes with significant drawbacks. The repeated string slicing and searching lead to inefficiencies, resulting in a time complexity of approximately n squared, where n is the length of the input string. This makes the brute force approach less suitable for large inputs, despite its simplicity. An alternative and more efficient method involves using a stack for iterative tree construction. The stack helps us maintain the hierarchy of nodes as we process the input string character by character. Here, the number of dashes before a node's value indicates its depth, which allows us to dynamically determine parent-child relationships. The core idea is that when the depth of the current node is less than or equal to the depth of the node on top of the stack, we pop the stack to move up the hierarchy until we find the appropriate parent. This eliminates the need for complex string slicing and enables us to process the input string linearly. The main advantage of this approach is its optimal time complexity of O(n), making it scalable for large inputs. However, it requires careful management of depth and values to ensure the tree is constructed accurately. Another option is a recursive parsing approach that improves upon the brute force method by avoiding repeated string slicing. Instead, we use a global index to traverse the input string, allowing us to parse it in a single pass. This makes the approach more efficient while still leveraging recursion, which naturally aligns with the tree's hierarchical structure. The global index makes it easier to track the current position in the string, streamlining the process of extracting node values and depths. While this method is efficient and avoids the overhead of maintaining a stack, it does introduce potential risks with recursion depth. For very deep trees, the recursion stack could exceed system limits, leading to stack overflow. Despite this limitation, its time complexity of O(n) matches that of the stack-based approach, making it a viable option in many scenarios. After evaluating the three approaches, the stack-based iterative method stands out as the most efficient and robust solution. This strategy is particularly well-suited for large inputs because it avoids the inefficiencies of brute force string operations and the recursion limit issues of the alternative recursive parsing method. With its linear time complexity, the stack-based approach ensures optimal performance even for long strings. The process involves traversing the input string character by character to extract node values and depths. Using a stack, we maintain the hierarchy of nodes, popping from the stack whenever the current depth is less than or equal to the depth of the node at the top. This allows us to dynamically assign the new node as the left or right child of the appropriate parent. Finally, the new node is pushed onto the stack. This method strikes the right balance between efficiency, scalability, and ease of implementation, making it the most practical choice for recovering a tree from preorder traversal. To solve this problem, we need to reconstruct a binary tree from a string that encodes its preorder traversal. In this representation, each node's value is preceded by a number of dashes that indicate its depth in the tree. The first step in our algorithm is to parse the input string. To do this, we initialize an index variable to traverse through the string and implement a helper function, read_value, to extract the depth and value of each node. The depth is determined by counting consecutive dashes starting from the current index, while the value is obtained by reading the numeric portion of the string that follows the dashes. After extracting this information, we update the index to point to the next unprocessed part of the string. Once the input is parsed, the next step involves recursively constructing the tree using the extracted depth and value information. In the recursive tree construction step, we define a helper function called build_tree that takes the expected depth of the current node as an argument. The base case for this function is straightforward: if the index exceeds the length of the string or if the depth of the current node does not match the expected depth, we return none. This ensures that nodes are placed at the correct levels in the tree. For the recursive steps, we first extract the depth and value of the current node, create a new tree node instance with this value, and then recursively call build_tree with an increment depth to construct the left and right subtrees. Once the subtrees are constructed, we return the current node to its parent. Finally, the tree construction process is initiated by calling build_tree with an expected depth of 0, which corresponds to the root node of the tree. A key insight that simplifies this algorithm is the way the input string encodes depth using dashes. This encoding allows us to naturally distinguish between parent and child nodes based on their depth. Additionally, since the input represents a preorder traversal, the root node is always encountered first, followed by its left and right subtrees in sequence. To process the string efficiently, we use a global index, which eliminates the need for backtracking and ensures a linear traversal of the input. For the tree structure, we use a tree node class that includes attributes for the node's value, left child and right child. While a stack could theoretically be used to track parent nodes, recursion makes this unnecessary. In terms of complexity, the algorithm processes each character in the input string exactly once, resulting in a time complexity of O(n). The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. When implementing this algorithm, it's important to handle various edge cases. For example, if the input string is empty, the function should return none. If the input represents a tree with just a single node, the result should be a tree containing only that node. Another scenario to consider is a completely skewed tree, where all nodes are either left children or right children. Lastly, if the input string contains invalid characters or does not follow the expected format, it should be validated before processing. To understand this algorithm in action, let's consider the input 1 2 3 4 5 6 7. We start by reading the root node with value 1 at depth 0. Then, at depth 1, we read the value 2 as the left child of the root. At depth 2, we read values 3 and 4 as the left and right children of node 2, respectively. Similarly, we construct the right subtree of the root with value 5 at depth 1, and its children, 6 and 7, at depth 2. This results in the final tree structure, where the root node 1 has 2 children, and each child has its own subtree. To solve the problem of recovering a tree from its preorder traversal, we start by defining the structure of our tree nodes. The tree node class has 3 attributes: val for the value of the node, and left and right for its children. Next, we define the recover from preorder method in the solution class. This method takes the traversal string as input and uses a stack to help reconstruct the tree. We initialize an empty stack and set the index to 0 to track our position in the string. The main portion of the function begins with a while loop that iterates through the traversal string. First, we calculate the depth of the current node by counting the number of consecutive dashes. Each dash corresponds to one level deeper in the tree. For each dash, we increment the depth variable and move the index forward. Once the depth is calculated, we proceed to extract the value of the node. We mark the starting position of the value and continue moving the index forward as long as the current character is a digit. After extracting the complete numeric value, we convert it to an integer. Using this value, we create a new tree node instance, which represents the current node in the tree. Now, we need to adjust the stack to match the depth of the current node. If the stack contains nodes from previous levels that are deeper than the current depth, we pop them off the stack. This ensures that the top of the stack always represents the parent node at the correct level. Once the stack is adjusted, we check if there's a parent node available by examining whether the stack is not empty. If a parent exists, we determine whether the new node should be attached as the left or the right child. If the parent node's left child is empty, we assign the new node to the left. Otherwise, we assign it to the right. After attaching the node to its parent, we push the current node onto the stack. This allows it to potentially become a parent for future nodes. Finally, after processing all characters in the traversal string, the root of the tree will be the first node in the stack. We return this root node as the output of the function. Here, we start by defining the tree node class, which represents the structure of a node in the binary tree. Each tree node has an integer value, as well as left and right child pointers, both initialized to null. Then, in the solution class, we begin implementing the recover from preorder method. This method takes a string traversal as input, representing the preorder traversal of the tree encoded with dashes to indicate depth. We also initialize a stack to help manage the nodes and an index variable to traverse the string. The while loop iterates through the string, and the first step inside is to calculate the depth of the current node by counting the number of consecutive dashes. This helps us understand how deep in the tree the current node should be placed. After determining the depth, we extract the value of the node from the traversal string. This involves identifying the starting position of the numeric value and using a loop to process all consecutive digits. We then convert this substring into an integer and create a new tree node with the extracted value. Next, we adjust the stack to match the depth of the current node by popping nodes until the stack size corresponds to the current depth. This ensures that the stack's top node is the immediate parent of the new node. If the stack is not empty, we attach the new node to its parent. Depending on whether the parent's left child is null, the new node is assigned as either the left or right child. Finally, the current node is pushed onto the stack, preparing it to become a potential parent for subsequent nodes. Once we've processed all characters in the traversal string, the loop ends. The root of the tree is the first node added to the stack, so we simply return the first element of the stack as the root. If the stack is empty, which should only occur for an empty input string, we return null. This completes the implementation of the recover from preorder method, reconstructing the tree from the preorder traversal string while respecting the depth information encoded with dashes. To begin solving this problem, we start with the input traversal string 1 2 3 4 5 6 7. The first step is to initialize our variables. We set up an empty stack to help us keep track of nodes as we build the tree, and an index variable initialized to 0, which helps us parse through the string. Now, we parse the first node. Since there are no dashes at the beginning of the string, the depth is 0. The value extracted is 1, so we create a new tree node with this value. This node becomes the root of our tree. We then push it onto the stack, which now contains only the root node. At this point, the root node tree node, 1, is successfully set up. Next, we parse the second node. This time, there is 1 dash before the value, indicating a depth of 1. The value extracted is 2, so we create a new tree node with this value. Since the depth is greater than the top of the stack, we attach this new node as the left child of the last node in the stack, which is tree node 1. Then, we push tree node 2 onto the stack. Moving on, we parse the third node. Here, there are 2 dashes, so the depth is 2. The value extracted is 3, and we create another tree node. This node is attached as the left child of tree node 2, the current top of the stack. We then push tree node 3 onto the stack. For the fourth node, we again encounter 2 dashes, indicating a depth of 2. The value is 4. Since the depth matches the previous node, we adjust the stack by popping tree node 3 to find the correct parent. We then attach tree node 4 as the right child of tree node 2 and push it onto the stack. Finally, for the fifth node, we see 1 dash, giving a depth of 1. The value extracted is 5, and we adjust the stack by popping both tree node 4 and tree node 2 to find its parent, tree node 1. Tree node 5 is then attached as the right child of tree node 1 and pushed onto the stack. Continuing, we apply the same process to the remaining nodes 6 and 7. Both are parsed and attached as the left and right children of tree node 5, respectively. Once all nodes are processed, the final tree structure is complete, and it looks like this. 1 is the root, with 2 and 5 as its left and right children, respectively. Under 2, we have 3 and 4 as its left and right children, while under 5, we have 6 and 7 as its left and right children. Now, let's explore another example using the input 1 2 3 4 5 6 7. Here, we begin by parsing the root node. The value extracted is 1, and we initialize the stack with tree node 1. Moving to the next node, we parse the value 2 at a depth of 1. The node with value 2 is attached as the left child of tree node 1, and we push it onto the stack. Next, we parse the value 3 at a depth of 2. This node is attached as the left child of tree node 2, and it is pushed onto the stack. For the value 4, we see a depth of 3. We create a new node and attach it as the left child of tree node 3. This node is also added to the stack. Now, for the value 5, there is a depth of 1. Since the depth is less than the current top of the stack, we adjust by popping nodes until reaching the appropriate parent, tree node 1. We then attach tree node 5 as the right child of tree node 1 and push it onto the stack. The final tree structure for this example is as follows. 1 is the root with 2 and 5 as its left and right children. Under 2, we have 3 as its left child, and under 3, we have 4 as its left child. Finally, 5 has 6 as its left child. Let's look at one final example with the input 1-40134990. We start by parsing the root node with the value 1. This node is added to the stack as the root. The next value is 401, which has a depth of 1. We create a node 4401 and attach it as the left child of tree node 1. This node is then added to the stack. For the value 349, the depth is 2. A new node is created and attached as the left child of tree node 401. This node is pushed onto the stack. Finally, the value 90 has a depth of 3. We create a new node and attach it as the left child of tree node 349, and it is added to the stack. The final tree structure for this example is 1 as the root, with 401 as its left child. Under 401, we have 349 as its left child, and under 349, we have 90 as its left child. This concludes the tree reconstruction process for this input. To analyze the time complexity of this solution, we start with parsing the input string. The algorithm processes the traversal string one character at a time using an index pointer. Each character is examined to either identify the depth, represented by dashes, or to extract the numeric value of a node. This extraction involves finding the start and end of the numeric substring, but since every character is visited only once, this step is linear in time, resulting in a total cost of O(n), where n is the length of the string. Next, we consider the stack operations. For each node, the algorithm adjusts the stack to reflect the current depth level. In the worst case, nodes may need to be popped from the stack repeatedly, but since each node is pushed and popped exactly once over the course of the traversal, the total cost of all stack operations is proportional to the number of nodes, or OK, where k represents the total number of nodes and is at most equal to n. Now looking at tree construction, attaching a node to its parent as either a left or right child is an operation that takes constant time. Since this operation is performed once per node, the total time cost for tree construction is OK, where k is the number of nodes. Summing up all these components, the overall time complexity of the solution is O(n), as the linear traversal of the input string dominates the computation, while stack operations in tree construction are proportional to the number of nodes, which itself is bounded by the input size. Moving on to space complexity, the first contributor is stack storage. The stack is used to maintain nodes at different depth levels during tree construction. In the worst-case scenario, such as when the tree is completely skewed, the stack holds all nodes, leading to a space requirement of OK, which is proportional to the number of nodes. This is the first factor influencing our space complexity. Next, we consider the space required to store the tree. Since the tree is constructed in memory and each node is represented as a tree node object requiring constant space, the total memory needed for the tree is proportional to the number of nodes, resulting in OK space. We also account for the temporary variables used in the algorithm, such as depth, value_start, and index. These variables occupy constant space, or O(1), and do not contribute significantly to the overall complexity. Combining all these factors, the total space complexity of the solution is OK, which can also be expressed as O(n), since the number of nodes is proportional to the length of the input string. To emphasize the efficiency of this approach, we compare it to a brute force method, which might involve multiple passes over the string or less efficient data structures for depth management. Such approaches could lead to O(n²) time complexity due to redundant computations. In contrast, the current solution is optimized with a single-pass string traversal and efficient stack operations, achieving O(n) time and space complexity. Finally, let's evaluate the best, average, and worst-case scenarios for this algorithm. In the best case, where the input string represents a balanced tree, the time complexity remains O(n), because each character is processed exactly once, and stack operations are limited to the tree depth. In the average case, with a randomly structured tree, the time complexity is still O(n), for the same reasons. Even in the worst case, where the tree is completely skewed, the algorithm maintains O(n) time complexity, as stack adjustments occur in O(1) amortized time per node. To mathematically justify this, note that each character in the string is processed once, and each node is pushed and popped from the stack exactly once. This ensures a total time complexity of O(n). Similarly, the space complexity is proportional to the number of nodes due to the stack and tree storage requirements, resulting in O(n) space. This efficiency is mathematically optimal given the constraints of the problem, making the solution both time and space optimal. When solving this problem, there are several common mistakes to watch out for. First, one of the most frequent issues is misinterpreting the depth from the input format. Remember that the number of dashes directly corresponds to the depth of the node in the tree. If this is not tracked carefully, the reconstructed tree could end up being incorrect. Another common mistake is incorrectly handling recursion. Without a well-defined base case or termination condition, recursive solutions can fail, potentially leading to infinite loops or incorrect results. For those working on an iterative approach, it's crucial to use a stack effectively. The stack helps track parent nodes at each depth, and omitting it can result in an improperly structured tree. Additionally, always account for edge cases. These include scenarios like an empty input string, a tree with only a single node, or irregular input formatting. Testing your solution against edge cases ensures robustness. Lastly, avoid inefficient parsing. Repeatedly slicing strings or scanning the input multiple times can significantly increase the time complexity. Instead, aim to process the string in a single pass for better performance. Now, let's consider some key insights relevant to interviews. This problem often evaluates your ability to perform depth-first reconstruction, which tests your understanding of recursive traversal and tree building techniques. Interviewers may also ask you to compare recursive and iterative approaches. For instance, recursive solutions come with a memory overhead proportional to the height of the tree, due to the call stack, whereas iterative solutions use an explicit stack, which can be more memory efficient. Be prepared to discuss optimization strategies, such as ensuring the string is parsed in O(n) time and managing node depth sufficiently. Another important aspect is edge case awareness. You should be ready to explain how your solution handles situations like malformed input or minimal input, for example, a single node tree. Additionally, this problem is related to others on LeetCode, like constructing binary trees from preorder and inorder or postorder traversals. Reviewing problems like LeetCode 105, 889, and 606 can help reinforce your understanding of tree reconstruction techniques and improve your performance in interviews. There are alternative approaches you can consider when solving this problem, each with its own advantages and trade-offs. One option is recursive parsing. This method processes the string directly based on the depth of the nodes and constructs the tree as it goes. It is intuitive and straightforward to implement, but it comes with the risk of stack overflow for very deep trees. Another approach is iterative parsing using a stack. Here, an explicit stack is used to manage parent nodes at each depth, which helps avoid recursion. While this method is more memory efficient, it requires careful management of depths to ensure correctness. A third option is two-pass parsing. In this approach, the string is parsed in one pass to determine the depths and values of the nodes, and the tree is built in a separate second pass. Although systematic, this method is less efficient than parsing and building the tree in a single pass. Each approach has trade-offs. Recursive solutions are easier to write and understand but come with higher memory overhead. Iterative solutions, on the other hand, are more memory efficient but can be trickier to debug and implement correctly. Great job! To summarize, we tackled the problem of reconstructing a binary tree from preorder traversal using a recursive approach. We discussed key concepts, strategies, and takeaways to help you succeed. If you enjoyed this session, don't forget to like and subscribe for more algorithm practice. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!